Section 5.2 is almost just a continuation, if you will, of 5.1. So in 5.1, we reintroduced logarithms, which you've seen before. And we talked about some of their properties, their graph, things like that. And then we looked at the differentiation, the properties of how we take a derivative of logarithms. So what we're going to do now is we're going to do the reverse. We're going to look at integration. Now, we're not looking at taking the integral of logs. That's not what we're doing. We will get to that later this semester, but that's not what this means. What we're going to do is we're just going to look at that rule in reverse. So this is the derivative rule that you've seen before. The derivative rule says when you have f of x equals the natural log of x, and the derivative is 1 over x, we get the following integration rule. So this is the integration rule. It's like the reverse of the derivative rule. What we did in the last section had this written down equivalently. Right? Looks something like that. If you take the derivative of natural log, you get 1 over x. Well, if you take the antiderivative of 1 over x, you should get natural log. But there's some absolute values that show up. And remember why those showed up? Logs have a domain that's only positive numbers, right? So whatever the values are that we are going to insert into our log, they better be positive, and so absolute value will eliminate that negative option. Still have to deal with zeros occasionally. We know we can't have that. But this gives us only the positive components. So what we're going to be working with now is we're going to be working with finding antiderivatives or doing integration where we have 1 over x involved somehow. Okay? So taking a look, this is the first one. Very basic. It's not 1 over x, it's 5 over x. Okay? So the easiest thing to forget in this case is the absolute values, so don't forget those. Natural log, I will have an absolute value of x. What am I going to do with the 5? It goes in front of the ln. All right, so let me remind you of that. You've seen it happen before, not with logarithms for what we've been doing, but it goes in front. This is equivalent to taking 5 times the integral of 1 over x dx. All right, 5 over x is the same as 5 times 1 over x. So the 5 goes in front, and I'm missing something. Plus c, very good. So I have 5 natural log of absolute value x, and then the plus c. And both of those are things that are easy to forget, the absolute values and the plus c. And that's it. That's the antiderivative. Okay, let's do another one, a little bit harder. What is it about this that makes this harder? The 4 minus what?
4 minus 3x.
Okay, I've got a 3x on bottom, and I've got the addition and subtraction there too, right? Okay, so if it were just the 3x, we could almost do it like the last problem here, where we could just pull like a 1/3 out in front, and we may see that happen later today. We do, in fact, in a moment here. But this one has more going on than just that. It also has that addition and subtraction. So if we were doing a derivative, we would say something like, this is basically like a chain rule problem, right? Do you remember sort of the reverse of chain rule issues when we were doing antiderivatives? It was the very last section that you learned in Calc 1 if you took it in this book. Yes, it's U substitution. Good job. All right, so we first are going to identify that this is going to be a U substitution problem. And it is, in fact, everything that's on bottom that's causing, if you will, the concern. So our U is 4 minus 3x. So we're going to take the derivative, and the notation that we usually jump to is to just write the du on the right, and we'll multiply to the dx to the other side in a minute here. What is the derivative of the 4 minus 3x? Yeah, just negative 3, and then it's dx, right? And then what we do is we multiply or divide, depending on which one we're working with. In this case, we're going to divide the divide the negative 3, or multiply by the negative 1/3 to the left. So I have negative 1/3 du is equal to dx. So this piece of information right here and this piece of information right here will allow us to make an appropriate substitution. So our substitution back up here will have a negative 1/3 in front. We'll have an integral. It will be 1 over u and du. And just as a reminder, what we're doing is here's that dx. It's being replaced by the negative 1/3 du. I put the negative 1/3 in front. I put the du in back. And then this piece on the bottom, 4 minus 3x, is being replaced by the u in the denominator. And this has the same form as the rule at the very beginning, or the property at the very beginning we looked at. So the negative 1/3 is here. What is the antiderivative of 1 over u? Good, natural log of absolute value of u. And then what do I need? Plus c. Now I'm not quite done with the problem. Why not? Right, if the problem started out with x, it needs to end with x. And right now it's got a u in it. So I need to change it back. So what is u?
4 minus 3x.
Right, it's 4 minus 3x. So we simply replace the u inside the absolute value, still with absolute values. And then we're done. Okay, so far so good? All right, let's try another one. It looks a little bit messier, but it's actually not any more difficult. Okay, so the reason this one looks messier is because we've got addition and subtraction on the bottom and on the top, right? Okay, so still, the only method that you have at your disposal, and I can't say this for too much longer, but for now, is use substitution. The other possibility is that you could do something with like long division. We did see that happen on occasion. If the use substitution didn't pan out for us, if there was something that wasn't working, or we recognized maybe the other earlier or something like that. But use substitution is sort of our go-to. So what would the u need to be in order for this to make sense? Right, it needs to be what's on the bottom for two reasons. Number one, the denominator needs to be where our variable is, right? Because if the variable's on top, what in the world are we going to have on bottom? Du? That's not possible. Okay, so that's one issue. The other issue is that the denominator has a higher exponent. And when you take the derivative of that higher exponent, it will become the lower exponent that's on top, or at least it stands a chance. Okay? So we're going to let the denominator be u, which is x cubed minus 3x squared. Now then, what is the derivative of x cubed minus 3x squared?
3x squared minus 6x. 3x cubed, or yeah, squared.
You're right, 3x squared minus 6x. And all of that is times dx. Now, that doesn't quite look like the numerator, but it's close. Good. If we divided it by 3, it would be right, wouldn't it? So we're going to divide by 3, or multiply by 1/3. So 1/3 du would in fact equal the x squared minus 2x dx, which is what we have right here. So all of that can now be replaced with 1/3 du. So I always write my 1/3 in front because I don't want to, mix it up with everything else. It just simplifies it in my mind. And I always write my du at the end. You could certainly write it on the top of the fraction, but you don't have to. I write a 1 on the top of my fraction. 1 du is the same thing as du. So I write my 1 on top, my du at the end. What's going to go in the denominator of this fraction? U, because that's what we let our u substitution be. So by 1/3, what's the antiderivative of 1 over u? Natural log absolute value u, and then I need my plus c, and then I need to change it back. What is u?
X cubed minus 4x.
Perfect. I don't think I have an example of what I'm about to say, but let's just pause for a moment and pretend that I had something inside that said like square root of 3x plus 2, okay, or something like that. I have a square root, like I had in the last lesson. I have a square root inside of my log. If I had that, you could pull out the 1/2. I mean, that would be okay. But even if you didn't, you wouldn't necessarily have to have the absolute value signs for it to be right. Why not? Right. So it's not because you can take the square root of negative, it's that you can't get a negative out of the square root. That would be in this case, right? I mean, both those are true statements, yeah. So sometimes you'll see those absolute value signs eliminated, like if you're checking an answer or if an answer comes back to you from WebAssign or something. Just be aware that if that's the case, check. It's probably something that they already know is positive, and you don't need the absolute values. It's just sort of like overkill to have them there, okay? All right, take a look at part D. Now on this one, if we let the denominator be u, that would not help the numerator at all, right? Because the numerator is what has the bigger exponent in this case. So on this one, u substitution is not the way to go, which means we're going to do long division. Okay? So long division, this is one of those algebra topics that, I don't know, people don't like them for some reason, but it mirrors regular division that you feel just fine with, so we're going to just pretend like you all love it. All right, so here's what we have underneath our underneath our division sign, and the x minus 2 is on the outside. Now whenever I do this, I only look at the very beginning of what I'm dividing by, which is x, and I ask myself these questions. I say, what do I need to multiply x by to get whatever the first term is what's underneath the division sign? So in this case, 2x squared. What would I need to multiply x by to get 2x squared? 2x. So I'm going to put 2x on top, and I'm going to do that multiplication. So I'm going to get the 2x squared, which was my whole purpose for choosing that. And then I need to multiply the 2x by the negative 2, which is going to give me minus 4x. Okay, so now with long division, the thing that you would do next is that you would change your signs. So you would switch the signs, and the reason is because you would subtract, right? If we were doing this with just whole numbers, you would be subtracting. It's equivalent to changing signs. So obviously these add to 0, which was the point. And then I have now 7x and 4x, which is 11x minus 3. And I do the same thing again. I say, what would I need to multiply x by to get 11x? And the answer would be, well, 11. So then I'm going to multiply 11x, and then I need 11 times negative 2, which is negative 22. And then I would change my signs. Again, the 11x's cancel out. And on this one, I'm left with 19. Remainder of 19. So sometimes students are not sure when to stop. You stop when the degree of the remainder is less than what you're dividing by, right? 19 is a constant. It has a degree of 0 is actually what we would call that. But x minus 2 has a degree of 1. That's the exponent, the highest exponent there is 1. So here's where we would have to stop, okay? And that's why we couldn't have stopped at like 11x, is because they both still had degree 1. All right, so this is not calculus, right? All we did was we rewrote, or we're about to rewrite, the original expression that we were given. And the original expression we were given is now going to be 2x plus 11, and then it's plus 19 over x minus 2 dx. And that's better than it was before, because much of that, 2/3 of that, is something that you could have done before you actually even learned the log rule that we did today, right? Yeah. So what is the antiderivative of 2x? Yep, x squared. And we're going to do the plus c at the very end, so I won't do it right now. What's the antiderivative of the 11? 11x. And then this part, this third part, is where that log is going to come into place. The 19 in the front is just like the 5 on our original first problem. It's going to go in front. And then I'm going to have a log of what? The absolute value of x minus 2. Now, technically, there's a u substitution here. It's just dreadfully boring, right? Because u is really the x minus 2, but that means that du is 1 dx, which means it's almost silly to actually do it because the derivative of the denominator is just 1. If it weren't, we'd need a u substitution for that part of it too. Okay? And then I need one more thing. Somebody already told me it before. The plus c. Okay, any questions on that one? Okay, I have one more. This one, which really looks like scary, because I just told you a minute ago that you do not have a rule to take an antiderivative of a natural log yet, right? And yet, this problem says antiderivative of natural log. So, any thoughts as to what we might do to actually avoid taking the antiderivative, but still be able to take the antiderivative of the whole thing? What you thinking, Nate?
Plug in what natural log of x is equal to 1 over x.
but it's not equal to that. Its derivative is that. What do you want to let u be? Yeah, that's what we want to do. Because whatever we let u be, we don't actually have to take that antiderivative, right? Yeah. And, you know, we can let the squared be on there if we want. We don't really need to. There's no reason to. So I'm just going to leave it off, I think, here, unless we come back to it later and decide that it's necessary for some reason. What would du be? Well, it'd be 1 over x dx. And why is that friendly? That's what's left in our problem. Now, if you can't see it very well, think about what's really going on here. This is the natural log of x, and it's squared. And it's times 1 over x, because that's what it means for it to be divided by x. And then we have the dx on the end. Okay, so this is the du that we just decided upon. And this piece in here is u. So I have the integral of u squared du. Is that what you have? Do you know what the antiderivative of u squared is? No. We're doing an antiderivative. 1/3 u to the third, or u to the third over 3 if you prefer. And then plus my c. And then what is u? The natural log of x. Okay, now this problem is complete. I want to sort of pinpoint an error that you might think you could do here without somebody actually saying it and you feeling like, oh, I should have realized this before, that I can't do that. Some of you might look at this and think, can't I bring the 3 to the front? Right, the 3 that's on the natural log of x, and the answer is no. The property of logs that allows you to bring the number to the front is if it had been the x cubed inside of the log. This cubed is on log. So the difference is that this is actually saying ln of x times ln of x times ln of x. Right, that's what this means. Whereas the other one that allows us to bring it to the front would be saying ln of x times x times x. Okay, so that's why that property isn't going to hold for us here. Okay, it looks kind of like the same thing, but those parentheses are really important. They make a difference. What's that?
You also then can't derive it to like backwards.
Correct. You're right. Okay. Some trig rules. So I'm going to have you jot these down. I ran out of space to put them the same way exactly that they are in your notes. But go ahead and write these down. You've seen these before, but it has probably been a while. After you've seen them today and put them into your notes, make sure you go back and put them into that antiderivative sheet that I gave you so that it's all kind of in one place. Did I mess something up? I did. There's a negative missing somewhere on the last one. This one should be negative. Make sure you get that negative in there. I was so worried about my spacing, I lost my negative. So the antiderivative of sine is negative cosine. The antiderivative of cosine is sine. Those two are easy ones to remember. The antiderivative of tangent is negative natural log cosine, absolute value cosine. And the antiderivative of cotangent is natural log of sine, absolute value sine. And then the secant is the natural log of absolute value secant plus tangent. And cosecant is the negative natural log of absolute value cosecant plus cotangent. All with plus c's, as I've written on here. All right, so we're going to do some practice with these. The first one is the integral of secant of x over 2. Okay, so you have an antiderivative form for the antiderivative of secant, but this one says x over 2. So what am I going to have to use in order to deal with the x over 2 part of it? U. I mean, it's a u substitution problem, much like the ones we were doing just a moment ago. So the u value will be the x over 2. There will come a day when you won't even think about that as a u substitution problem, and you'll just do it automatically inside of the regular problem. Probably most of you are not there yet, so we're going to keep writing it out. Okay? What's the du for this? What's the derivative of x over 2? I'm not asking a trick question, I promise I'm not. It's 1/2, yeah. It's just the coefficient part of it, the 1/2. dx. And we don't have a 1/2 dx in our problem, which means that that 1/2 needs to move. So what will dx equal? 2 du. We're going to have to multiply it to the other side. So this can be rewritten as 2 times the integral. The secant didn't go anywhere, so don't go deleting too much. It's secant still, but it's the secant of u, and then the dx is replaced by the du at the end, the 2 at the front. 2 is a part of the problem. What is the antiderivative form for secant? It's one of the fun ones. The natural log. Yep, secant of u plus tangent of u. I'll close my absolute value and then plus c. And then the last step's to do what? Yeah, plug in u as the x over 2. So this is 2 natural log of secant of x over 2 plus tangent of x over 2 plus c. Okay, does that make sense? Nice. Now we've got sines and cosines on top and bottom. I'm pretty sure that the last section of Calc 1 actually has a problem that's the same problem. What in the world now? Well, let me tell you something you can't do. Because there's addition and subtraction on the bottom rather, instead of on top, we can't sort of separate this in any way. Like if this had been 1 plus sine on top and cosine on bottom, like if it had been the reciprocal of what you're seeing, you might be able to separate this and use some trig, like turning sine over cosine into tangent or something like that. And that could be a really good way to do it. But with the addition on the bottom of the problem, you can't do those things. So you have your hands tied. There's nothing you can do with cool trig tricks. Okay? What's the last thing you have to do then? Gotta be use substitution. It's the only thing there is, right? What in the, shocker, I know. What in the world are we going to let our u be? 1 plus the sine, in this case it's t, the variable in this problem, sine of t. In your homework and stuff, if you like if you're turning something in or a test or whatever, I tend to use x's, and if I used a t and you switched it into x's, that'd be fine. I'm going to guess inside of WebAssign you need to be careful with your notation. If it starts out t and you put an x, it's probably going to count you wrong. So just be watchful of your variable that they use that you use it to. Okay. All right, here though, we're in good shape. And here's where the fun starts because you're taking a derivative, and I just told you antiderivative. So what's the derivative of 1 plus sine of t? Is it positive or is it negative? It's positive. This one's positive, yeah. So this one's cosine of t dt. And that happens to be what we have in the numerator exactly. If it weren't, we'd add or we would multiply or divide like we have been doing. But this one's exactly what we have in our numerator. So this can be rewritten as 1 over u du. I think probably when we did it in Calc 1, the denominator was probably squared because we couldn't have taken this antiderivative in Calc 1. So we didn't have the rule to do it yet. So we do now, though. What is the antiderivative of 1 over u? Yeah, it's log. Natural log, absolute value of u, and then plus c. Okay, then. What was u? 1 plus the sine of t. Now, it's fine if you leave it this way, but those absolute values are not needed anymore. Why not? What are the range values? What outputs do you get from sine? From 1 to negative 1, right? It's going to go up and down between 1 and negative 1. But what does that plus 1 inside the absolute values do? It's going to shift it all up 1, which means now the sine, the inside of what the log is going to be oscillating between 0 and 2, right? It's shifted up. So it would be perfectly acceptable on this one to not have the absolute values, you'd still need parentheses because there's still addition going on in there. But you very well might see this as an answer instead. If you were, say, checking it back at the book, or if WebAssign, freaks out with the absolute values, it might want the parentheses instead on something that they're not necessary on. Okay? All right, we have one last problem to do. It says to evaluate the definite integral. So, here's what we have. Definite integrals means that it has the limits of integration, right? That's the difference. It means in the very end of this problem, we're going to get a numerical answer. We're not going to have a plus c. We're going to actually have a number, or we're going to have something that is a number but with maybe an e in it or something like that. It looks maybe like it has an e in it, but it's not going to have a variable in it, okay? So we start the same way though, yes? Yes. What are we going to have to do to get the antiderivative of this problem? Use substitution. You guys are going to get so good at use substitution. What will u be? Has to be what's on top, 1 plus the natural log of x, because we do not have a form yet for finding the antiderivative natural log. So then, what's the derivative of 1 plus the natural log of x? 1 over x dx. All right. Now, there's a catch. We're doing use substitution in the middle of a definite integral. Do you remember what the catch is?
You have to change it to like u is in between those, and that you have to switch the definite integral.
Yeah, these limits of integration are the limits of integration for x. So either leave them off, that's what I usually do, or you have to evaluate your u equals 1 plus natural log of x and figure out what they should be changed to. I tend to leave them off because it mirrors the other process a little bit more closely. So for me, I leave them off for now. So I'm not going to put the limits of integration up there for now. I'll put them back in a minute. And I'm going to pretend like the problem is an indefinite integral problem. So right now that gives me u squared on top. Well, and then du over here, because this piece, all of this, with the 1 over x, if you will, is the du part. Okay, so what is the antiderivative of u squared? 1/3 u cubed. And we would have a plus c, but we're really going to have numbers plugged in here in a minute, so we're not going to put the plus c on here. But we do want to take this back to what u is. U is supposed to be 1 plus the natural log of x. So instead of having the u cubed here, I'm going to have 1 plus the natural log of x cubed. And then I can do my evaluation at the original values. E is on top, 1 is on bottom. Right. The fundamental theorem of calculus says we can plug in the top value first, so 1 plus the natural log of e, quantity cubed, minus 1/3 times 1 plus the natural log of 1, quantity cubed. What is the natural log of e? It's 1. So inside the first set of parentheses, we have 1 plus 1, which is 2. And 2 cubed is 8 times the 1/3 in front gives me 8/3. The second one, natural log of 1, is 0. So I have 1 plus 0, so I get 1. And 1 cubed is 1. And then 1 times the 1/3 is 1/3. So this is 8/3 minus 1/3 for a grand total of 7/3. All right, any questions on those? Awesome.